Assume that a procedure yields a binomial distribution with n equals 55 trials, and the probability of success for one trial is p equals 0.74. Find the mean for this binomial distribution. Well, to work a problem like this, what we have to use are simple formulas: mu equals n times p, and sigma equals the square root of n times p times q. So, normally to get a mean and a standard deviation of a probability distribution, we have to put the outcomes in L1, the probabilities in L2, and use one-var stats L1, L2. But in the case of a binomial, with all these assumptions that we make with binomials, that there's only two outcomes, that each outcome is independent, and so forth, this filters through the formula for calculating the mean and standard deviation, and the result are these two formulas. So all we have to do for the mean is just identify the number of trials, which is 55, and the probability of success on any given trial, which is 0.74, and then multiply. So 55 times 0.74, that is 40.7. The standard deviation would be the square root of n, which is 55, times p, which is 0.74, times q. And you do have to remember that q is always just the complement of p. So 0.74, and you can write this in as 1 minus 0.74 if you like, that's fine. Or you could calculate it outright. Either way, 0.26 is what it is. So we would take the square root of 55 times 0.74 times, and if you do the 1 minus 0.74, put it in parentheses, or you don't need parentheses around the 0.26. So 3.25. So it says to 2 decimals. We'll go with that. 3.25. Next, will the probability histogram for the binomial random variable be approximately bell-shaped? Well, the rule for being bell-shaped is, in some textbooks, it's n times p times q must be greater than or equal to 10. For other textbooks, it's n times p is greater than or equal to 5, and n times q is greater than or equal to 5. They don't always give the same result, but they're doing the same thing. They're just telling you what the values of n and p and q must be so that you get approximately bell-shaped distribution. So we'll answer with this form here. And effectively, we just need to come up with the value of n times p times q, which we sort of just did. We just, in the standard deviation, we just didn't actually square it. Or I'm sorry, we took the square root of it. So we went from the variance to the standard deviation. So this is effectively just the variance. So we need to compute this. So it would be 55 times 0.74. Oops. 4, that is, and times 0.26. So 55 times 0.74 times 0.26, we get 10.58. And that certainly is greater than 10. And since it's greater than 10, we can be assured that this is a bell-shaped distribution. So n times p times q, and I'm saying q rather than 1 minus p, but it's q is 1 minus p, is greater than or equal to 10. So that is the case. If you want to see why that would be the situation, then let's take a look at the histogram of this distribution. So we have 55 trials, probability of success on any given trial is 0.74. And I'll just change this from 0 up to 55 and just shade the whole thing. That's fine. That's what the distribution looks like, the probability distribution for the binomial. Now, if I put a normal distribution curve on top of that, then the normal distribution curve fits this distribution very well. So what that means is the normal distribution is a very good approximator to the binomial distribution that we're looking at here. So when you know about finding probabilities for a normal distribution, if this is the case, then you can actually use normal distribution probability calculations in place of binomial distributions because it's such a good approximation.